In this video, we're going to finish up chapter 12. We're going to find the derivative of y equals e to the x, the exponential. This is from chapter 12 of Master Math Mentors AP Calculus AB manual that we are using. So if we look at e to the x, it seems that this function doesn't really fit any of the rules that we've learned in the past. Product rule, quotient rule, trig. It's not natural log. It's not a power rule. It's not a power because the x is in the exponent, not the number being in the exponent. So we'll use our calculator to help us decide. So in your calculator in Y1, I typed in e to the x. The E button can be found over on the left-hand side. 1, 2, 3 buttons up, but you got to hit the second button first. So I put that in Y1, and then in Y2, we put in Math 8, and we typed in e to the x inside the, or d dx. Inside the parentheses, we put e to the x, and down at the bottom, x equals x. And then if we looked at a table of those values from -4 to 4, I've already filled them in for you here just to save some time, but you should pause this video and fill those values in. But what do we notice about e to the x and the derivative of e to the x? So e to the x and the derivative of e to the x. We notice that all of those values are exactly the same, literally exactly the same. So what can we say? We can say that the derivative of e to the x is also e to the x. This is actually really cool because this is one of the only functions that the derivative is also the original function. That normally does not happen, but this is really cool that it does happen. There's tons of memes out there. Go look them up, derivative of e to the x memes, and you'll find plenty. We can actually prove this, and I'm going to try to do that for you in this box. Y equals e to the x is called logarithmic differentiation. While you might not necessarily need to know how to do this, it's cool to see. So we're going to take natural log of both sides, natural log of y, and natural log of e to the x. We're going to use some properties here. We can move this x in front. So we get natural log of y equals x times ln of e, using those natural log rules. Looking at this idea, natural log of e, what does that really mean? That really means that log base e of e is equal to what? So what we're looking at is e to what power? Remember, log just gives us the exponent. E to what power is equal to e? And the only rational answer there would be 1. So on the left side, we get ln of y, and on the right side, we get x times 1, which is just x. And then we can do some implicit differentiation. Derivative of ln of y is 1 over y dy dx, and derivative of x is just 1. We can cross multiply or multiply both sides by y. If we multiply both sides by y, we get dy dx by itself, and dy dx is just equal to y. But back up here, what do we say y was equal to? We said y was equal to e to the x. So dy dx is equal to e to the x. So using logarithmic differentiation, we have proven that the derivative of e to the x is also e to the x. We could also use chain rule with this. E to some power, it could be anything. It doesn't just have to be x. The derivative of that is equal to e to that same power. We're not going to change that power. And then we're going to multiply it by the derivative of whatever is in that exponent, probably some function of x. So let's take some derivatives. We're going to use a chain rule a good bit on these. So y prime, e to the something. The derivative of e to the something is just e to the something times the derivative of that something. And derivative of 5x in this case is just 5. We would normally write that in front of the e to the x. 4e to the 1 minus 2x, the derivative of that would be 4e to the 1 minus 2x times the derivative of the 1 minus 2x piece, and that is -2. And we can multiply the 4 and the -2 together, and we get -8 e to the 1 minus 2x is our derivative. Number 21, y equals e to the 1 over x. We can probably want to rewrite that as e to the x to the -1, e to the x to the -1, 1 over x. And then we can take the derivative of that. Y prime would be e to the x to the -1 times the derivative of x to the -1 ddx of x to the -1st power. So I'm going to change this x to the -1 back to 1 over x just to make it look a little bit nicer. And then x to the -1 derivative of that is going to be -1 x to the -2. We're going to make that -2 positive by moving it to the denominator. So we get -1 e to the 1 over x. So negative e to the 1 over x divided by x squared. And we are rocking and rolling. Number 22, y equals e to the square root of x, 2 times e to the square root of x. We can write this 2 times e, x to the 1/2. So if we take the derivative, we're going to get 2 times e, nothing's changing. And then we're going to multiply that by the derivative of x to the 1/2. The derivative of x to the 1/2 is 1/2 x to the -1/2. These twos cancel. We can move the x to the -1/2 to the denominator to make it positive, and we can change it back to a square root if we so choose. So we get e to the square root of x all over square root of x. Obviously, we can leave it x to the 1/2 power if we would like. Looking at this next part, what if it's not just e? And the derivative of e also, e to the x also follows this rule, and we'll talk about that in a second. But the derivative in more general terms, I guess, the derivative of any number raised to the x power is equal to a to the x power, that same expression, times the natural log of that base, the natural log of a in this case. So this is actually the general expression for all exponentials, including e. So if you were a function of x, we would just use chain rule. So we have the same thing, and then we're going to take the derivative of u, whatever u is, some function of x probably. So does this work for e to the x as well? So d dx of e to the x, the answer is yes. This also works for e to the x. It's e to the x ln of e, but like we talked about earlier, ln of e is just 1. It just happens to be 1. It's the only one, the only input that we can put into the natural log that does give us 1. So we do get e to the x. Any other base besides e is not going to produce that outcome. But this is also true for e to the x, not just any. All right, so derivative of 2 to the x would be 2 to the x times the natural log of the base, and the natural log of the base is 2. And we could leave it just like that. We don't have to rearrange it. We could rearrange it, but we don't necessarily have to. 24, we have a base of 5. So our derivative is going to be equal to the exact same thing that we're looking at times the natural log of the base. And then we also have to multiply that by the derivative of the exponent, 3x plus 1. Derivative of 3x plus 1 is just 3. I'm going to go ahead and move it to the front. We can't actually multiply it by the 5 because the 5 is being raised to the exponent, 3x plus 1. So we actually can't multiply those two things together. So don't try. We're going to get ln of 5. 25, we get y equals 6 to the x squared plus 2x minus 1. So y prime would be that exact same thing, 6 to the x squared plus 2x minus 1. We got to multiply that by the natural log of the base, natural log of 6. And we also have to multiply that by the derivative of this x squared plus 2x minus 1 piece. And the derivative of that would be 2x plus 2. Does it really matter what order we rearrange this in? Not really. 2x plus 2 we can put in front. 6 to the x squared plus 2x minus 1, and then ln of 6. I don't think it really matters what order it's in, but that's the order that the answer key has it in. All right, 26, we get 1/4 raised to the x. This is going to be y prime. It's going to be 1/4 raised to the x times the natural log of 1/4. And that would be the final answer. We could leave it like that, but using some properties of logs, we could try to rearrange this a little bit. This 1 raised to the x, 4 to the x, so that'd be 1 to the x all over 4 to the x. 1 to the x is just 1, and this natural log of 1 over 4 would be equal to ln of 1 minus ln of 4. ln of 1 is this idea of log base e of 1 is equal to what? And remember, logs give us the exponent, so e to what power is equal to 1? And that's only 0, so this ln of 1 is equal to 0. 1 to the x is equal to 1, so we get 1 over 4 to the x times negative ln of 4. I probably wouldn't change it any more than that, but 4 is equal to 2 squared, so we can get all sorts of fancy with this. So we get negative ln of 2 squared over 4 raised to the x, and then we can actually move that 2, that exponent, in front. So we get negative 2, ln of 2 on top, and 4 raised to the x in the denominator. So just some algebraic techniques there. I think this answer is probably sufficient, the one that I just circled. So we've learned a lot about taking derivatives up to this point. And by a lot, I mean a lot. We've learned a lot. So at this point, we have a box here that I would probably take a picture of, put it on my cell phone, something where you have easy access to this. This is every derivative rule that we've learned up to this point. And it uses this idea of chain rule. So the u to the n or f of u, g of u, that's just saying that you may have something other than just x inside the function. And then we're going to have to multiply that by the derivative of whatever that something inside the x is. So it's just using chain rule notation there. But I would definitely put that in a safe place where I could look at it later. All right, we got a couple more problems here to work out. I might not do all of these, but I'll do the majority of them. Number 27, y equals e to the x plus 3 raised to the third power. This is power rule. We're going to move the 3 in front. We're going to subtract 1, and then we're going to multiply by the derivative of the inside. And the inside is this e to the x plus 3. So we get 3 y prime is equal to 3 times e to the x plus 3. 3 minus 1 is 2 times the derivative of e to the x is e to the x. And derivative of 3 is 0. How could we rewrite this? We could possibly put the e to the x in the front, maybe. Make it look a little bit better. So this would be 3 e to the x times e to the x plus 3 squared. Number 28, we have a product, even though it does have exponential e to the x. It is not exponential rule solely. It is product rule because we have an f and a g. So y prime, derivative of x, we got f prime g plus g prime f. Derivative of x is 1. G stays the same. Derivative of g prime is e to the x times x. Clean that up a little bit. We can factor an e to the x out maybe if you wanted to. So if we factor that e to the x out, we're left with 1 plus x. It's probably about as nice as you can get it. Number 29, wherever it went. Way up here probably. Number 29 is trig. We have sine on the outside. So we're going to take derivative of sine, which is cosine e to the x. And then we have to multiply that by the derivative of e to the x, which is just e to the x. Typically, you might write the e to the x in front. Number 30, this is e to the x rule. So y prime is going to be e to the whatever the exponent is times the derivative of that exponent, which is cosine x. (31), this is ln rule, because ln is the outside function. Remember, derivative of natural log is 1 over whatever's inside, x plus e to the x, times the derivative of that inside. Derivative of x is 1. Derivative of e to the x is just e to the x. So we get 1 plus e to the x all over x plus e to the x. Number 32, this is either going to be quotient rule or product rule. We can make it product rule. E to the 4x times x to the negative 1. And now it's product rule. If you would like to do that, I'm just going to practice quotient rule because it's probably a good idea just to practice that. Low d high minus high d low all over low squared. All right, so low is x. Derivative of e to the 4x is e to the 4x times the derivative of 4x is 4 minus high e to the 4x times derivative of the low is 1 all over x squared. If we were to clean this up a little bit, we could factor an e to the 4x out of the numerator. So we get e to the 4x. We factor that out. We're left with a 4x. We're left with a 4x, and on this one, we're just left with a minus 1 all over x squared. Number 33, we got x over e to the 4x. So same idea. We could write this as x times e to the negative 4x if we wanted, and then use product rule. However, I'm just going to use quotient rule. So same idea as the previous problem. The low is e to the 4x. The derivative of the top is 1 minus the derivative of e to the 4x. Yeah, I just messed that all up. Low d high minus high. The top is x times the derivative of e to the 4x will be e to the 4x times the derivative of 4x will be 4 all over e to the 4x quantity squared. In this case, we're going to multiply these exponents, the 4x and the 2, an exponent raised to an exponent, you multiply. And we have a e to the 4x and e to the 4x in common on top. So just like we did on the last problem, we can factor that out. E to the 4x, we're left with a 1 essentially, minus an x and a 4. So 1 minus 4x. And then in the denominator, we're going to multiply the 4x and the 2. So we get e to the 8x. So we are done with number 33. Number 34, we're looking at e to the x under the cube roots. We can rewrite this as e to the x raised to the 1/3 power, or since that's an exponent, it doesn't matter where the exponent is on this inside. This exponent could also be right there. So we could go ahead and write this as e to the x over 3, which is the same as 1/3 x. So y prime would be equal to e to the x over 3 times the derivative of x over 3. The derivative of x over 3, that's really just 1/3 x. And the derivative of that is really just 1/3. So we get e to the x over 3 all over 3, which we can change back to the cubed root of e to the x. if we would like, all over 3. We could also write it, instead of writing it all over 3, we can put 1/3 in front. That's the same thing. I said I wasn't doing all these, but here we are. I've done most of them. Might as well keep going. If you feel like you don't need to watch them, like you're good, feel free to start on your homework. X to the 10th times 10 x squared. This is product rule. F prime g plus g prime f. Derivative of f prime, the derivative of x to the 10 is 10x to the 9th. We're not going to change the 10x squared. Plus, we're not going to change the x to the 10th this time, but we are going to change the derivative. The derivative of 10 x to the second is 10 x to the second times the natural log of the base is 10, times the derivative of x squared is 2x. Now, what do we have going on here? We got a lot going on here. And I actually wrote this x squared in the wrong place. This should be 10. Oh, man. This should be 10 raised to the x squared, not 10x squared. What can we do here to simplify this? We can possibly multiply the x to the 10th and the 2x together. That's really the only thing I see. So we get 2x to the 11th, 10 raised to the x squared, natural log of 10. And over here, we got 10x to the 9th times 10 raised to the x to the second. Now, there are some common factors floating around in here. We got a 10x to the second and a 10x to the second. And we do have a common factor of 2 between the 2 and the 10. Between the x and the 11th and the x to the 9th, we have a common factor of x to the we have a common factor of x to the 9th. So we could factor out a 2x to the 9th times a 10x squared. And if we take that away from this first part, 10 divided by 2 is 5. That's the only thing that's going to be left. X to the 9th, we factored out x to the 9th. 10x squared, we factored out the 10x squared. We factored out the 2x to the 11th. We have an x squared left over. And we have an ln of 10 left over. We factored everything else out. So that's just some GCF work. Number 36, y equals secant squared. Man, why does it keep doing this? I don't know. I must have hit a button that scrolls it down for some reason. Number 36, y equals secant squared. So this would be trig. Derivative of secant squared is secant tangent. That's going to be fun to write out. Derivative of secant. Actually, it's power rule. Yeah, this is actually power rule, because when it says secant squared, it's actually this entire thing being raised to the second power. So if you can do a problem like this, you have a pretty good grasp on what's going on as far as taking derivatives is concerned. So power rule, we're going to bring the exponent 2. We're going to multiply it in front to secant. All of this stuff on the inside, ln of 4x squared plus 2 to the first power times. Now we're going to take the derivative of all of this stuff. The derivative of secant is secant tangent. Derivative of secant is secant tangent. So we get secant of ln of 4x squared plus 2 tangent. I'm going to run out of room, I'm sure, of ln of 4x squared plus 2. And now we're almost there. We're going to take derivative of this ln of 4x squared plus 2. Derivative of that is 1 over 4x squared plus 2. And derivative of 4x squared plus 2, this is just chain rule over and over and over again, is 8x. Derivative of natural log is 1 over, and what's ever inside times the derivative of that. So we got a lot of stuff here. So at this point, we do have two factors of secant. We got the secant ln, and we have another secant ln. We have a 2 and an 8x we can multiply together. And then we can also factor a 2 out of the denominator. So I'm going to go ahead and do this all at once. We can factor this 2 out. We're left with an x squared plus 1. 8 divided by 2 is 4. And 4 times 2 is 8. And we have a factor of x left over. So we end up with 8x divided by, there should be a 2 in front of that x squared. 2x squared plus 1. My bad. When I factor this 2 out, the 4 divided by 2 would be a 2. There should be a 2 in front of that x squared. So 8x all over 2x squared plus 1. We do have two factors of secant. So it's going to be secant squared ln of 4x squared plus 1. And then our tangent of ln 4x squared plus 1 would be our final derivative answer. Not too bad. Alrighty, we could also do implicit differentiation with e to the x and natural log in this case. There's both. This first part is going to give me a product rule. So derivative of x is 1 times e to the y. I did not take the derivative of y that time, so it'd be actually 1 dx plus x times the derivative of e to the y is e to the y. But since we're doing implicit differentiation, we have to be ensured to include the dy dx. Derivative of 8x is just 8 minus 3 ln of y. That's going to be 3 over y dy dx. And derivative of 0 is 0. And now we got to solve for dy dx. Anything that has a dy dx, I'm going to leave on the left. And actually, I'm going to multiply through by y to clear out that denominator. That way I don't have fractions inside fractions. So we can go ahead and do that at this point. It would make things a lot easier if we were to multiply everything by y at this point. So if we multiply everything by y, we get y e to the y plus xy e to the y dy dx plus 8y minus, if we multiply this term by y, the y's are going to cancel. That's what we wanted, dy dx. And 0 times y is just 0. All right, so anything that has a dy dx, we're going to leave over here. So all this stuff stays. The minus y e to the y goes over here. And the minus 8y, or the 8y, gets moved to the other side. So we get x, y, e to the y, x, y, e to the y, dy dx, minus 3 dy dx is equal to negative 8y minus y e to the y. We can now factor the dy dx out. So they both have a common factor, dy dx. That's our algebraic trick here. That's going to help us get dy dx by itself. Xy e to the y minus 3 equals negative 8y minus y e to the y. We can divide both sides by xy e to the y minus 3. Divide both sides by xy e to the y minus 3. And we end up with our final answer, maybe, dy dx is equal to negative 8y. Let's go ahead and factor a negative out of that. We get negative 8y negative, parentheses, 8y plus y e to the y. And let's go ahead and factor a negative out of the bottom. The 3 is going to become positive, and the xy e to the y is going to become negative. So I just switched the order so that the positive term would be first, and then the negatives cancel just so we don't have so many negatives. We have 1 negative now instead of 3. So it's just a little bit nicer. 38, we're looking for some type of pattern here. If they ask you to find the 20th derivative, they are not asking us to go through and do this 20 times. However, we could, but they're not asking us to do that. The derivative of e to the x is e to the x. negative e to the negative x. The derivative of that would be negative e to the negative x times negative 1, which would be e to the x plus e to the negative x. And f double prime of x, derivative of e to the x is e to the x. Derivative of e to the negative x is e to the negative x times the derivative of negative x, which is negative 1. And that equals e to the x minus e to the negative x. And we see that pattern has started over. So every even derivative is going to be equal to the original function. Also, the second derivative. So the second derivative, the fourth derivative, the sixth derivative, all gets us back to the original function, which is e to the x minus e to the negative x. So the 20th derivative would also be e to the x minus e to the negative x. And that concludes chapter 12. We have learned almost everything we need to learn about taking derivatives. We're going to start applying that now in the next few chapters. Chapter 13, we're going to learn how to take derivatives of inverse functions. But after that, it's all application of derivatives. So we need to make sure we have a really good, solid understanding of how to take derivatives before we move forward. Because once we move forward, it's going to be under the understanding that you know how to take a derivative. If you have any questions, please let me know. You can send me an email or a message on Remind, and I'll get back to you as soon as I can. Have a great week.